Hello and welcome back to the lecture on multicollinearity. So in the previous lecture we explained the concept of multicollinearity and we said in case of perfect collinearity there are some problem, the equation, there is an error that occurs and often the software cannot run regression, but there are some other softwares they can actually omit some variables and run the regression. Now a question may appear that why exactly, like how can I mathematically understand what this problem is occurring. So we have said in case of different examples where the sort of perfect linear relationship is a problem because the coefficients are varying simultaneously. Now, if I want to sort of try to explain that in terms of the beta coefficient in a generic term, so we'll see why this problem is occurring. Let me first write down the expression of a beta coefficient when I have more than one explanatory variable, and let's take the case of two explanatory variable. So I'll write it down. So beta 2 is going to be, in this case, summation where, okay, let me actually write down the equation first. So y is equal to, so let's say the same notation that we are using, beta 1 plus beta 2 x2 plus beta 3 x3 and some error term. Okay, so this is my equation. Now, in this equation, if I write it down, let's say the value of beta coefficient in terms of x2 and x3, so it will be like this. So you have to basically you get this value by solving this the same least square method you have to adopt, and if you do that, x2i minus x2 bar into y I minus y bar. So I have not memorized it, and I don't recommend you to memorize it. Neither you have to actually solve this. You don't have to do it on your own. It is just for the purpose of illustration that if I have something like this square, and then I will have just the same way x3 I minus x3 bar into, all this has to be y bar into x2 I minus, sorry about this small 4, and it's set to be square. It's just a symmetric way of writing. The first term and the second term are symmetric, just I have changed 2 and 3, okay. And the denominator is going to be, x2i minus x2 bar square x3i minus x3 bar square minus, it's a bit of a big equation, okay, but anytime you are running, like you are going beyond the simple OLS where you are incorporating more than one explanatory variable, it is going to look like a bit messy. But the purpose of writing this equation is not for you to remember this equation, but only for you to sort of understand why the perfect collinearity problem is occurring, okay. And it's good to have some idea about how it looks like, the value of beta 2 when I have like more than one explanatory variable. So if I have 3, it will be even more messy. So x3i minus x3 bar, and then there will be a close bracket, and then there will be a whole square. So, it is a pretty big term. Now, the reason, so let me actually name the equations, number the equations. So, let us say this is my equation 1 and this is my equation 2. Now, for B2 I got these values, and if I have to get the B3, I just have to simply change the values of x2 with x3, right. Now, let us have the case where I have my x2 and x3 are perfectly linearly related. Let us say this is equal to mu x2, okay. This is my equation 3. Now, if I substitute this value x3 with x2, putting 3 into 2 into equation 2, what I will find, I will find this both term in the numerator is going to be 0 as well as in the denominator that is going to be 0, okay, and it is going to be undefined. And this proof you can actually find from the Christopher Dougherty's textbook. It is a good idea to in the chapter of chapter 3 when it is in the page number around 160 to 170, it talks about the problem of multicollinearity. So, there you can see the proof is given. So, you can actually take a look why why the value of beta 2 becomes undefined here, all right. So, that is basically the proof of why perfect collinearity is a problem for simple OLS, for the OLS regression. Okay, with this we will end this lecture.